Welcome to Optimization 2. So we've got a little road to hoe here. Maybe I'll get a little more chalk. May need it. I'm already on the second row of my new box. All right, here's the situation. We're going to be faced with a real valued function defined on Rn, n-dimensional vectors. And for the purposes of this talk, we'll talk about R2. And in general, we'll do R2 and R3. They get more complicated the higher this goes, more steps. But this is sort of the easiest step. We'll also be given a region. And the types of regions we'll be given are polygonal regions like triangles and rectangles and so on. I gave you an oriented rectangle, I think something like 0, 2 cross 1, 3, a square. We'll also be given a triangle, things like that. And we'll want to find the maximas and minimas, the optimum values for f on a particular region. I want to show you how to do that. So let me change the region from this square to a triangle. And the triangle I'll use I'll just specify the vertices. Just making something up here. We want to be able to do a couple things. We want to be able to graph f over the region R. And we'll want to be able to solve equations for variable vectors that are in our region. And this, I think, we're in pretty good shape. I've got, if you open up the two documents that I gave you, one of them is a template sort of describing how, in very brief detail, what we're doing here. And the second one gives you a little code and some problems to work on. So for examples. But the first step in doing this is to find the critical values. And these are called the global critical values. Of f over r. So to do this, the method is easy. You take the derivative and you set it equal to 0 and solve. Now this may give you some values that are not in your domain. So this domain, saying x and y is in R, is part of the definition of the function. So the function will consist of an equation, and it will consist of, this should be this, R. It'll consist of an equation, and it'll consist of a restriction, and that is part of the definition of the function. So we solve this for values x and y in the region that we're given. And this derivative, because this is a real valued function, this derivative is called the gradient. So this is the first part. Solve for those. That gives you the critical values, global critical values over the region. The next part, this is sort of plug and chug. You can use Mathematica to solve too. The next part is the boundary. Check the boundary of R. The boundary of R has it's like the partial derivative symbol. But in this case, where we have a triangle, the boundary consists of 4 line segments. I'm just going to take a quick graph of this. Radiant red here, new one. 1, 2, 4, 7. Let's make this not 4, 7. Let's make this 4, 1. So there is our triangular region R that we're dealing with for this problem. And I want to know how to describe the boundary. The boundary consists of 4 segments. Segment 1, segment 2, and segment 3. They all work the same. So let's do that. So I'm going to erase the board now, and we're going to work on F restricted just to the segments. If you wanted to check an example, you could look at one of those, not the template version, but the other version, and you could use that function and enter this triangle instead of the one that I've got there and see what it looks like. So F on segment 1. The first thing to do here is to parameterize segment 1. That is, describe segment 1 as the range of a function of one variable. So segment 1 goes between 0, 0 and 1, 2. So let's call it seg1. Seg1 of t equals a point on 0, 0 plus t times the direction. The direction is 1, 2. So this is just t to t. 0 less than or equal to t less than or equal to 1. Without this restriction, it defines the whole line. With this restriction, it defines exactly the line segment between these two. And what we want to look at is we want to optimize F on or F of segment 1 of t. 0 less than or equal to t less than or equal to 1. So that's what we want to do. I'm going to erase up on top maybe. So how do you do this? This is a one-dimensional problem. If you plug segment 1 formula into F, you just got one variable. So this is the one we want to find. So this is F composed with the seg1 function evaluated at t. We want to take the derivative, set it equal to 0, and solve. This was very different from what we've done before. This just gives you the function on that line segment. And when we do this, we will find critical points, not global critical points, but critical points of the segment, of F on the segment. So this is what you want to do. It will give you the critical points. And they will be points of the segment. It doesn't actually give you critical points. It gives you some t values. Maybe a t value, I'm making this up now because I don't really have a function, maybe a t value of 0.3 and a t value of 0.7. Those are the critical values of that function, F composed with segment 1. And these yield points of the plane, of the triangle, of the boundary of the triangle, segment 1 of 0.3 and segment 1 of 0.4. Now, segment 1 of 0.3 is equal to segment 1 of t was t to t So segment 1 of 0.3 is the ordered pair 0.3 and 0.6. And segment 1 of the other made up critical value is 0.4, 0.8. These lie on segment 1, and these are possibilities for the maxes and the mins. And again, if we draw segment 1 was between 0, 0 and 1, 2. So there is segment 1. This function describes segment 1. And the 2 points we have are 0.3, 0.6. So 0.3 and 0.6. So there's one of them. And the other one is 0.4. I have 0.7 here. So what happened here? Can't read my own writing. It should have been segment 1 of 0.7, which would be 0.7, 1.4. And so the second one is 0.7, 1.4. These are possibilities for the maximum. In this triangle that we have here, we may have critical values, global critical values. There, a max or a min can occur, but a max and min can also occur on the boundary at critical points of the boundary. So there are 2 other points. There are 2 other, so we have found the critical values on the boundary, but we also have to check the endpoints. Now these correspond to the endpoints of our domain, t equals 0 and t equal 1, and they will correspond to these points, these corner points of the triangle. So we will have 2 critical values that we'll need to check, 0.3 and 0.7 corresponding to these points. And then we have 2 endpoints, and that will be segment 1 of 0, which is the origin, 0, 0, and segment 1 of 1, which is the second point, 1, 2. This handles this one part of the boundary. We still have 2 segments to go. So the boundary, doing this job on the boundary consists of sort of a one-dimensional optimization on each portion of the boundary. On each portion, you must find the critical points and the endpoints. Now, the top end point of the first segment is the beginning endpoint of the second segment, so there are only 3 of them to check. But these points will always be possibilities for optima, maxima or minima. So now we have all our critical points. Let's pretend we have all our critical points. We've done it for all 3 segments of the boundary. We have 3 parameterizations to do. But now we are done with the global critical points, and we are finished with the boundary critical points. There's a third step, and that's to chart all of these or list everything. So we make a list of, these are the list of the points. We're just interested in the points now, not the parameterization that gave us these points. And from part 1, we have critical values. I'm going to just make these up, like maybe 0.8, 0.3, and 0.6, and maybe 2.1, 0.6, something like this. These are inside that triangle. Part 2, we also have some critical values. We had the 0.3, 0.6, and we had the 0.7, 1.4, also just completely made up values. And now we want to find f of those points. So we make the entire list. This was just on segment 1. But we also have segment 2 and segment 3 where we have to list those, if any. We also have the boundary points. 0, 0 was 1. 1, 2 was 1. So we have a whole list of points here. And now we plug each of those into the function. And we get some values. 3, minus 1, 2, 1, 6, and so on. Just like in one dimension, perusing this list, this is a complete list of the possibilities for where the maximum and the minimum occur. The maximum will be the largest of these. This one occurred on the boundary. The minimum is the least of these. This one occurred at an internal critical point. And this gives the full optimization, the way to find total maxes and mins. We didn't find local maxes and mins. Up here, these are candidates for local max. Only these global ones are candidates for local maxes and mins globally. And here we have a second derivative test. We check the determinant of the second derivative, the Hessian, and this second derivative test will tell you whether or not these points are local maxes, local mins, or inflection points. On the other hand, this test can fail. So just like in the second derivative test for one variable, it might not tell you anything. But this is the full optimization problem. As dimensions continue, the critical point is absolutely, the global critical points are the easiest part by far. It is this finding the critical values on the boundary. Find the points on the boundary to check that becomes difficult. And the difficult part of that is the parameterization of the boundary. We won't do a whole lot with it, but we will parameterize several types of boundaries. And I wanted to just say a little bit about that. First of all, the easiest type is the type we started with, which is oriented rectangles. Here, the so-called graph parameterization works. One of the variables is constant, the other one you just leave as it is. So for a vertical line, x is fixed, y varies between two numbers, so this is easiest. The first type where you have to do something is on polygons, not necessarily oriented. And in polygons, the boundary consists of line segments. And these are pretty straightforward, because the line between 2 points is something we can do. And then there's a restriction on the variable t, which will just give you this. So these are fairly straightforward to do, these line segments. Parameterizing line segments. Unfortunately, a polygon can have many sides, so this can be a tedious process. But these are pretty straightforward, we can do. Two other types we'll do are disks. A disk is a circle with the inside. So it's fairly easy to find a Cartesian equation for one of these. Let's say the radius is little r. So if the radius is r, then this would be x minus x naught squared plus y minus y naught squared equals r squared. But a parameterization for this in terms of two variables, a full circle, is also not very hard. You can take your x coordinate to be equal to x naught, this variable, plus r times the cosine of t, or theta, and y to be equal to y naught, plus r times the sine of theta. And if you want the full circle, 0 less than or equal to t less than or equal to 2 pi. So you begin at x naught, y naught, and then the rest is similar, but instead of just cosine theta, sine theta, you have an r. So the full parameterization, alpha of t, is x naught plus r cosine t x naught, y naught plus r sine t, 0 less than or equal to t less than or equal to 2 pi. So this is the parameterization for any boundary of a disk. This just gives this boundary. And the fourth one that we'll look at is similar, boundary of elliptical regions. And in this case, an elliptical region is the same as a disk, except it has an x radius and a y radius, and they differ. So you have two radii. You have an x radius, and you have a y radius, and these might be the same or they might differ. But this is the parameterization then for elliptical region. So if the x radius is 3, this number would be 3. R is not a variable here. And if the y radius is 6, then this number would be 6. And so for an elliptical boundary, what happened here? Oh, this was a y naught. So for the elliptical boundary, it's very similar to the disk, the boundary of a disk, but a little different with the two radii. So what I'd like you to do right after watching this, or maybe during this, is to work the problems on the sheet that I have. And I gave you a little code which helps you do these. The first part is finding optimum in a square or a rectangle that's oriented. The second one has you do the same thing, maxes and mins, in a triangle. And that's what the homework's going to be like for the next time. It's all going to, these all work with one function, so that you have 4 problems with one function. So the critical values, the global critical values, are the same for each. You have to check whether or not they fit in your region or not. In any case, we'll work these over on Monday. Look at the graphing. The graphing is also a little different, but it's interesting. And it's interesting that you can graph these over regions, and you can play around with that a little bit. I'll see you Monday. Have a great weekend.